All right, we're back in business here, working on homework 2.2. All right, so the first question here says, to use the given graph of a function to sketch its derivative. So what I'm going to do is I'm going to kind of transpose the derivative onto this graph. And I'll start by looking at the points that are kind of easy to get. If I look at this value that corresponds to this value of x, the slope of the tangent line here is flat, it's 0, which means our derivative's value, okay, here would be 0. So I would put a red dot there on the x-axis. So the slope here is 0, which means that the derivative is 0. All right. Now another important point that I can see is this one here. It looks like the slope of the tangent line there is also 0, which means that I can put a 0 here. Now, the rest of this is just going to take some approximation. We're not going to be able to get exact numbers necessarily, but we'll be able to kind of see, like estimate what the values are. So let me see if there's another place where I can look where the derivative might be somewhat obvious. So let me try right here. It looks like the slope of that tangent line there looks like a perfect diagonal, which would mean that the slope of the tangent line there would be 1. So I need to kind of just, determine what 1 is here. So I'm just going to act like this is 1 right here. So that means that I would have a dot there. Now, let's take a look at what's happening in this little interval right here. In this interval, the slopes of my tangent lines are always going to be positive, but as I'm moving to the right, they're kind of decreasing as far as the slope is concerned, and it's approaching, so smaller slopes, smaller values, and then eventually it becomes 0, which means my red graph, which the slope, at the origin was 1, is going to stay positive, but it's going to approach 0. So it's going to do something like that. Those are positive values approaching 0. And then once I get past this point, what happens is that my slopes are negative, 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 and then they start to kind of straighten out a little bit here, and they look like they're getting closer and closer to becoming flat, but they're still sloped down slightly. So that means they're negative numbers, but they're getting smaller. So I'm going to have my derivative will be negative values, and then it looks like those negative values are getting smaller and smaller and smaller. So it'll look something like that. Now on the back side here, let's look in here now. Notice that my slopes, again, are positive, right? They're positive. But then back here, they're flattening out towards 0. So again, my derivative is going to be positive values getting closer and closer to 0, like that. And then when I pick something over here, my slopes are negative, right? Negative, negative, and it looks like they're starting to flatten out again to get closer to 0. So my derivative should be negative values and then getting closer and closer to 0. So the red one is what we're looking for. So let's see what they have as options here. Can't be this one. This one looks really good. This one, no. And this one, no. So it's going to be this one right here. All right. Whoa. Scrolled way too much there. Let's see if this is number 2. Okay, here we go. The graphs of 4 derivatives are given below. Match the graph of each function in A through D with the graph of its derivative in 1 through 4. So let me try and match this graph right here with one of these. All right, so let's start again here. I have slope of tangent line is 0 here, so about here I should have a dot. And then slope of tangent line here is 0, so here I should have a dot. I have positive slopes, positive slopes, positive slopes, positive slopes, and then they flatten out towards 0 here, and they flatten out towards 0 here. So I should have positive slopes, and they should go to 0 on both ends there. This is very much like the problem we just did. Then we have negative slopes, and they get steeper and steeper and steeper, which means the negative values get bigger and bigger and bigger. So it should do something like that. Then on the other side, same thing, negative slope, negative slope, negative slope. And as I move to the left, these get really steep, which means that the negative values get bigger and bigger and bigger. So it's looking like for A, that one matches up with 3. All right, let's take a look at the next one. This one's interesting. Slope here is positive, but notice it's a straight line. So those slopes are always exactly the same. So the slope of this looks like it's 1. And then all of a sudden at this point right here, it switches from being 1 to a negative slope, and that looks like -1. Perfect diagonal, but negative. And then when it gets to this point, it switches again and becomes a positive slope, and it looks like a slope of 1 again. So what happens is that our derivative looks like it has a positive. I'm going to say this is 1 right here. Looks like our derivative is positive here, 1. Then it switches to -1. Let's just say here, until I get to here, and then it switches back up to +1. So for that one, looks like B is going to be this one right here. Now we put open holes here because what's happening is at these corner points, our derivative is undefined because it's a corner. We can't have derivatives at corners. All right, let's take this one right here. So notice at this point, right here, our slope of our tangent line is 0. So that means that the derivative is 0 there. To the left, I have positive slope, positive slope, positive slope, positive, and they're getting less steep, and it looks like they're approaching 0. So I will have from 0, I will have positive slope, but then those slopes are getting smaller and smaller and smaller, getting closer and closer to 0. Now on the other side, I have negative slope, negative slope, negative slope, negative slope, but they're getting flatter and flatter and flatter also, which means that they're getting closer and closer to 0. So I have negative slope, but then it gets flatter and flatter and flatter, and so it approaches 0. So that one looks like it's 2. So 2 here matches up with this one. And then, of course, the last one, but I'll show you why. So notice here it has to be 0, here has to be 0, here has to be 0. So my derivative should have a 0 here, 0 here, 0 here. Let's see. On this piece right in here, my slopes are negative. So I know that my slopes have to be negative, so derivative has to be negative. Over here, my slopes are positive, so I know my derivative has to be positive, and it has to go back to that point. Over here on this side, all my slopes are negative, and they're getting steeper and steeper, which means the negative value has to go down. And then on this side over here, right, my slopes are positive, which means that my derivative must be positive, and they're getting steeper and steeper as I move to the left, so it should go up forever. So this one matches with this one. All right. Number 3, trace or copy the graph of the given function, and then use the methods of this example to sketch this below. So I'm going to use the same sort of idea that we've been using. Notice up here, slope of tangent line is 0, so derivative has to be 0. To the right of this, I've got negative, negative. They're flattening out, so it's negative, but they're getting closer to 0. So negative values, but they're getting closer to 0 as I move out. And then to the left side, I have I have positive slopes, and they're getting steeper and steeper and steeper, which means that the value of derivative is getting bigger and bigger and bigger. So I'm going to have positive slopes, which means derivative is positive values, and they get bigger. So it's going to look like this, which looks like this one right here. Okay. Same thing. Whoa, don't want that. So let's see what's happening here. We have, on this piece, we have a constant slope, and it's negative. So it's going to be something like this. And then we have, on this piece, a constant slope, and it's positive. So it jumps from being negative to positive. So that looks like this. And then we jump again, and we have negative. So that looks like this. And then we jump again, and it looks like we have positive, so it looks like that. Now, do any of these others do that? No, this one's kind of close, but this one went positive, negative, positive, negative. we had negative, positive, negative, positive. When I say that, remember, I'm talking about the slope. Negative slope, positive slope, negative slope, positive slope. So this is the one. All right, so what's happening here? This one's a little bit tricky. Notice as I move from left to right, I have a positive slope, then it's getting steeper and steeper and steeper and steeper and steeper. And remember, as I get to this point here, my derivative wants to become vertical. Remember, the slope of a vertical line is undefined. So my derivative, if I draw this, my derivative starts out and it has, let's say about right here, it has some value. Oh, sorry, it's positive, other side. So my derivative is positive. And as I move to the right, the derivative is still positive, but they get bigger and bigger and bigger, which means as I get closer and closer, the derivative values get bigger and bigger. But as I get to that green dot, it becomes undefined, so I can't actually cross over there. Now, on the other side, my slopes over here are also positive, right? Positive slopes. But as I move towards the origin, they're positive and they get steeper and steeper and steeper, which means, again, the derivative gets bigger and bigger and bigger. So over here, I've got some positive number for my derivative, and as I move to the left, they get bigger, bigger, bigger and bigger positive, which means I look like that. So my derivative actually has an asymptote right down the middle. My derivative does. So it will look like this one here. Okay, rechargeable battery is plugged into a charger. The graph shows C of t, the percentage of full capacity that the battery reaches as a function of time elapsed in hours. So you plug the battery in, 0% to 100% charge. Here's hours. So what happens is you plug in, it starts charging. It's charging very quickly. And then as time goes on, it slows down, right? The slopes of the tangent lines tell you, right, how fast it's charging at that instant. So it slows down as you get to the top, as you go longer and longer. So what is the meaning of the derivative? Well, derivative is the average rate of change. No, it's not an average. Total percent of full capacity? No. The elapsed time in hours? No. Instantaneous rate of change of percent of full capacity? Yes, instantaneous rate of change. That's what a derivative is. It's an instantaneous rate of change. In this case, of the percentage versus time, which was in hours. So we had the percentage over here versus time here. And then it says sketch the derivative. So what was happening here? In the very beginning, I started charging, and it was just a very, very steep derivative, right? So big positive derivative, big positive, and then as I go across, it's still positive, but they're not quite as steep. They're actually approaching 0. So I should start off with a big positive number, which this one looks like it is. And then as I move on, it's still positive, but it's going to be smaller positive until I get to 0, and it approaches 0. Are those my only options? Yeah, so it's this one right here. Oh, no, I have more options. Well, it can't be this one. These are negative values, and my derivative is positive. Here it starts at 0, and then they get bigger. That's not what was happening, right? I didn't start. My first derivative over here wasn't 0. It was very steep, so very big positive. So this is the answer right here. Let me see. What does the graph C prime of x tell you? All right. It tells us that, okay, let's read through this. The graph of C prime t tells us that the rate of change of the percentage of full capacity is increasing and approaching 100. It tells us that the rate of change is increasing without bound. It tells us that the rate of change of the percentage is increasing, approaching 0. That the rate of change is decreasing, approaching 0. And last one, decreasing without bound. It's going to be this one right here. Now, the reason why is what's happening is with the derivative is that the rate of change, right, the derivative is decreasing. So as I'm going to look back up, and it's approaching 0. So the one that we said it was, what's happening is we're looking at the derivative here. As we move to the right, we start out positive. It is decreasing. It is going down and down and down and down, and it is approaching 0. That's what the derivative is doing, right? So the rate of change of the percent charge is decreasing, approaching 0. Just so you know the difference between these pictures. This would mean the derivative was increasing and approaching some value, 100%. This one would be increasing and approaching 0, and this one would be increasing without bound. All right. Let's see, that's the answer. All right, find the derivative of the function using definition of the derivative. All right, state the domain of the function, and then state the domain of its derivative. So let me try and work this one out. All right, so I think what I'll do is for the derivative, I'm going to use limit h goes to 0 of f of x plus h, so 1/5 x plus h minus 1/4 minus f of x, which was 1/5 x minus 1/4 all over h. Now, hopefully you've done that so many times you understand what I'm doing there. I will distribute through the 1/5 here. So this is limit h goes to 0, 1/5 x plus 1/5 h minus 1/4 minus 1/5 x plus 1/4 all over h. And then cancel the 1/5 x's, cancel the 1/4. Notice all I'm left with is this. These h's will cancel, and I'm left with 1/5 without even having to let h go to 0. I just get this constant. All right, so state the domain of the function f of x. Well, this function is linear, right? It's just a line. And so I can plug any number I want in here. So the domain would be everything from -infinity to infinity. And then state the domain of its derivative. Well, the derivative is a constant, which means if we graphed it, the derivative would look like this. 1/5, it would just be a flat line, and it would go in both directions forever. So obviously the domain of that is everything, because it's defined everywhere. So -infinity to infinity. All right, find the derivative of this one. So I don't think I'm going to work through the derivative. I'm going to let you do that on your own. But what you would get is 5x minus 1. Now, once you get that, we look back domain. This is a parabola, and parabolas are defined everywhere. So the domain is everything. And since the derivative is a line, it again is defined everywhere. All right, now we start to get something more interesting. So let's find the derivative of this one. You know what? I think what I'll do, because I don't feel like doing all these derivatives, because we've done enough, I hope, that you understand how to do that now. Let me just get to the solution for you here. Let's take a look at this. Okay, so you go through, you set up your derivative, and then remember you do all that, get a common denominator, and then you come in with that conjugate, clean everything up, and then you get this right here, either this or this. Now, I think I'll write this one down on the other paper. -7 over t times 2 root t. -7 over t times 2 root t. Is that what I had? Yeah. Okay, so once we have that, let's talk about the domain of the function. Well, this right here, this function has a square root in it, and it has a fraction. So we got to make sure that that denominator is never 0. So if you let t be 0, you get 0 on the bottom, and then it's undefined. So t can't be 0. Also, you can't take the square root of a negative number. So we need to make sure that that t is always greater than 0, right? Can't be 0 or else you have division by 0. Has to be also positive in order for us to be able to take a square root. So the domain of the original function is everything from 0 to infinity. Now, as far as the derivative, look at the derivative. We have the exact same thing. T can't be 0 or else that'll be 0. And then also, t must be bigger than 0 because you can't take square root of a negative number. So the domain of our derivative will be exactly the same in this case as the function itself. All right, if we take the derivative here, let me see here. This will be -1 over 2 square root of 9 minus x. That's what you would get if you take the derivative of that. So again, I'm not going to go through the work. I'll show you the work just so you have it. Okay, so here it is. They use this definition of the derivative. Then they write it out. Then they come through with the conjugate. Go ahead and simplify, and at the end you get this. Now let's talk domain. Okay, the original function here is just a square root function. So I need to make sure that the 9 minus x is greater than or equal to 0. So right now I'm doing this one. All right. Now remember, you can have 0 here. It's okay because square root of 0 is 0. In the previous problems, we couldn't have 0 under the root because it was in a fraction. So you couldn't have 0 down here, or else you had division by 0. Here it's all right. So I need 9 minus x to be greater than or equal to 0. I can just add x to both sides. And that means x has to be smaller than or equal to 9, which means that I can have anything all the way up to 9, including 9. That's domain of the original function. Now, the difference between that and the derivative is that with derivative now, this appears in the denominator, so this cannot be 0. So I need to make sure that 9 minus x is strictly greater than 0 in the derivative. Right, so I'm talking derivative now. And move the x over and you get this, 9 is bigger than x, which means that the domain is everything to the left of 9, not including 9, so I put a parenthesis around it instead of a bracket. So that's the main thing to see, is that the difference here, bracket, we could have 9 here because it's well defined, but down on the bottom one we could not have 9 or else we'd have division by 0. All right, derivative of this one. So I have the answer right here below, so let's just look at it. Using this definition, you plug things in. Okay, once you plug things in, you get a common denominator, which is going to be a bit of a task. You get your common denominator, you clean up the numerator, which is a big mess. Distribute through this negative. You get this. Factor an h out of everything. Cancel these h's, and you get this, which is -7 over 2 plus t squared. So let's talk a little bit about the domain of this original one. The only problem that we ever have to worry about with domain of the original function is that we got to make sure that 2 plus t is not 0, or else we divide by 0. So t cannot be equal to -2. So that means that we should have everything except -2. The way we say that, -infinity to -2, do not include -2, unioned with -2, not including -2 to infinity. So that's basically the entire number line with -2 taken out and everything to the left and right forever. Now, what about the domain of the derivative? So the derivative was this. And notice here again, we don't want this to be 0, or else we divide by 0. So if we set this equal to 0, 2 plus t equals 0, we get t equals -2 again. So the only thing we can't have is t is -2, which means that our domain of our derivative is exactly the same, right, as this. Okay, derivative of this one. So if you take derivative of this one, this will give you 8x cubed. And since this is a polynomial, the domain is everything. And then, of course, the derivative is also a polynomial, so domain is everything. Do we care to see the work for that one? Let's see. Wondering why they had a printout. It doesn't seem like it would be that much work. Yeah, it's not that much work. But here it is. I'll get my hand out of the way for a second. That's what it would be. Okay, my hand. I don't even have a hand. I have a mouse. All right. When the graph of f is given, state the numbers at which f is not differentiable. So remember, anywhere we have jumps, anywhere we have corners or cusps, we cannot have a derivative. So here, that's, let's see, -4. And then here at 0, we have a jump. So those are the two places it's not differentiable. Okay, state numbers where it's not differentiable. Well, anywhere we have an asymptote, okay, is also a point we have to be concerned about. So here we have an asymptote from both sides. So at 0, it's not differentiable. And then again, at 3, we have this cusp. So 3. Okay, here we have a vertical tangent line. Vertical tangent lines are the slope of a vertical line is undefined. Therefore, we can't, the derivative, it's not differentiable there. So -1 looks like that's where that happens. And then let's see, everything else is okay until I get to, again, this cusp. That happens at 4. All right, here we have a jump at -1, jump in the graph. Can't differentiate there. And then again, we have a cusp here at 2. All right, that's it. That worked out pretty well. Hope that made sense.